Have you ever seen one of those massive container ships out on the ocean? Basically a floating city of steel, and just wondered, how in the world does that thing not just tip over? It feels like it should be impossible. Well, let's get into it, because the science behind it is this incredible, constant battle against nature itself.
So that's really the heart of the question, right? How does something that weighs hundreds of thousands of tons get tossed around by the ocean and somehow, almost magically, always snap back upright?
Well, it's not one single thing. The secret is this beautifully balanced dance between two massive opposing forces and one single, invisible point that is the absolute obsession of every naval architect. So, let's break this down.
Okay, first, let's meet the two main players in this drama. You've got the non-stop downward pull of gravity and the equally powerful upward push of buoyancy from the water.
It all starts out pretty simple. Every single ship has what's called a center of gravity. We'll call it G. And that's just the average point where all of its weight is pushing straight down. At the same time, the water is pushing back up through a point called the center of buoyancy, or B. That's the geometric center of the part of the ship that's underwater. Now, on a perfectly calm day, G and B are lined up, one right on top of the other. Gravity pulls down, buoyancy pushes up, and the ship just sits there, perfectly happy and upright. But what is the ocean ever perfectly calm?
Right, so what happens the second a wave comes along and messes up that perfect alignment? This is where the real genius of ship design kicks in.
The moment the ship tilts or heels over, look what happens to the shape of the hull in the water. One side digs in deeper, the other side lifts up. Since the underwater shape has changed, its center, the center of buoyancy, has to move too. It slides from its original spot, B, over to a new spot, B1, toward the side that's now deeper. But here's the key. The center of gravity, G, doesn't move. The ship's weight hasn't changed, so G is stuck right where it was.
And this tiny shift changes everything. Now you've got gravity pushing down through G and buoyancy pushing up through B1. They're not in line anymore. They've created a lever. Engineers call it a couple, and it's trying to turn the ship. The big question is, which way is it going to turn? Well, that all depends on our next key player.
So, is that turning force going to save the ship? Or is it going to sink it? To answer that, we have to talk about that invisible point I mentioned, the one that decides everything, the metacenter. The metacenter, or just M, is a theoretical point. When the ship tilts, that new upward force of buoyancy from B1 shoots up in a straight line. Where that line crosses the ship's original center line, that point is M. And the location of M relative to G is without a doubt the most important factor for whether a ship stays afloat. And here's the magic trick. If that metacenter, M, is located above the center of gravity, G, that turning force we talked about becomes a righting force. It creates what's called a righting lever that literally pulls the ship back upright. This is exactly what you want. This is a stable ship. So, the rule of thumb is incredibly simple. M above G, you're good. The ship saves itself. But if M ever drops below G, that same turning force suddenly works against the ship, pushing it over even more until it capsizes. That is a catastrophe. And if they land in the exact same spot, the ship just stays tilted, which, as you can imagine, is also a really bad day at sea.
Okay, so we know why a ship is stable. It's all about M being above G. But how do we measure how much stability it has? I mean, how powerful is that self-correcting force really? We can actually measure that power, and we call it the righting lever, or GZ. It's simply the horizontal distance between that downward push of gravity and the upward push of buoyancy. The bigger that GZ distance is, the more muscle the ship has to heave itself back to an upright position.
And yep, there's even a formula for it, at least for small angles. The righting lever, GZ, equals GM times the sine of the angle of heel. Now, GM is just the distance between our two VIPs, G and M. So all this formula is really telling us is something pretty intuitive. The bigger the gap between G and M, the more powerful your righting lever is going to be.
Now, naval architects take all of this data and put it into one incredibly important graph that tells the ship's life story when it comes to stability. It's called the GZ curve, and it shows you exactly how much righting power a ship has at any given angle of tilt.
And you can tell so much from just a glance. How steep it is at the beginning tells you its initial stability. The peak of the curve? That's the angle where the ship is fighting its absolute hardest to get back upright. And where the curve falls back to zero? That's the point of no return. That's the capsize angle.
The whole area underneath the curve represents the ship's stamina, its raw ability to soak up energy from the wind and waves. So that's all the theory. It's neat, it's tidy, but the real world out on the ocean is anything but tidy. It's chaotic. So how does this play out for real? Well, things can get really, really dangerous when the rhythm of the waves starts to sync up with the natural rhythm of the ship itself. It's like pushing someone on a swing. If you get the timing just right, they go higher and higher, and it can get out of control. And this dangerous resonance has a name: parametric rolling. As the source Tricky Mariner explains, it's a specific kind of rolling that's caused by the ship's own front-to-back pitching motion, and it's a huge issue for a lot of modern container ships.
So here's how it works. Picture a big container ship. It's got a super narrow, fine bow to cut through the waves efficiently, but a really wide, flat stern to hold more cargo. As the ship pitches up and down in the waves, think about what's happening. When that wide stern plunges into a wave, the ship suddenly has tons of stability, a huge righting lever. But a moment later, when the ship pitches forward and its narrow bow goes into the water, it suddenly has very little stability. So you get this crazy fluctuation: super stable, not stable, super stable, not stable. If the timing of that fluctuation matches the ship's natural side-to-side roll period, the rolls can build up to absolutely terrifying angles.
And that's the key here. It's not about how big the waves are anymore, it's all about the rhythm. This resonance can amplify the roll to a point that seems totally impossible for the weather conditions, leading to lost cargo, structural damage, or even capsizing the ship. So, I think the big takeaway is this: keeping a ship upright isn't a static set-it-and-forget-it deal. It's a living, breathing, dynamic dance between the ship's design, how it's loaded, and the wild, unpredictable physics of the sea.
And that kind of leaves you with one final big question. As we push the limits of engineering to build even bigger and more specialized ships, we're also creating brand new, unforeseen challenges in this ancient fight to stay upright. You have to wonder, what's the next parametric rolling? That's the kind of question that keeps naval architects working late into the night.